On a sweltering summer day in late July 2003, something unusual taxied out onto the runway at Cecil Field, a former naval air station sitting on the eastern edge of Jacksonville, Florida. To the casual observer, it might have looked like just another F-5 fighter jet preparing for takeoff. But anyone with even a passing familiarity with military aircraft would have immediately recognized that something was profoundly different about this particular machine. The aircraft wore a brilliant white paint scheme instead of the typical military grey or camouflage. Along its fuselage ran two distinctive pinstripes, one red and one blue, each angled sharply like the characteristic shape of a sonic boom pressure wave, and most strikingly, the nose of this F-5 had been dramatically transformed. Where a standard F-5E Tiger II featured a relatively sleek, pointed nose designed for high-speed combat operations, this aircraft sported an enormous bulbous proboscis that extended forward and downward, giving it an appearance that engineers and pilots alike couldn't help but compare to a pelican's beak. Beneath its fuselage hung an equally prominent fairing, a smooth aerodynamic structure that further enhanced the bird-like comparison. This was no ordinary F-5E. This was the Shaped Sonic Boom Demonstrator, a one-of-a-kind research aircraft that represented the culmination of decades of theoretical work, months of intensive design effort, and the collaborative expertise of some of the finest aeronautical minds in the nation. Over the coming weeks and months, this peculiar-looking airplane would help prove something that many had long suspected, but no one had definitively demonstrated in actual flight conditions, that the shape of an aircraft could be deliberately designed to reduce the intensity of the sonic boom it created when flying faster than the speed of sound. The implications of such a demonstration extended far beyond the academic interest of aerospace engineers. If aircraft could be designed to generate quieter sonic booms, it might finally become possible to lift the decades-old ban on supersonic flight over land. Commercial aviation could enter a new era where passengers might routinely cross continents and oceans in a fraction of the time currently required. Military planners could envision new capabilities for rapid response and strategic reach. The entire architecture of global transportation could be reimagined, but before any of that could happen, someone had to prove that boom shaping actually worked in the real world, with a real aircraft, flying through real atmospheric conditions at genuine supersonic speeds. That's exactly what the Shaped Sonic Boom Demonstrator was built to do. The thunder that shook a nation. To understand why the Shaped Sonic Boom Demonstrator mattered, we need to go back to the 1950s and 60s, when sonic booms first became a significant public concern. The physics of sonic booms had been understood, at least in broad terms, since the earliest days of supersonic flight. When Captain Charles Yeager broke the sound barrier in the Bell X-1 on October 14, 1947, over the high desert of what would become Edwards Air Force Base in California, he didn't just make aviation history. He also created the first documented sonic boom heard by ground observers, a sharp double crack that rolled across the Mojave like thunder from a cloudless sky. The sound itself is the result of a fascinating physical phenomenon. As an aircraft moves through the air, it pushes air molecules out of its path. These molecules, in turn, push against other molecules, creating pressure waves that propagate outward at the speed of sound. When an aircraft is flying slower than sound, these pressure waves can move ahead of the aircraft, allowing the air to smoothly flow around the approaching plane. It's somewhat analogous to the way water moves aside for a boat traveling at moderate speeds. But when an aircraft accelerates to the speed of sound, something dramatic happens. The pressure waves can no longer get out ahead of the aircraft. Instead, they begin to pile up, coalescing into a shock wave that extends from the nose of the aircraft in a cone shape, trailing behind it like the wake of a boat. This is often called a Mach cone, and everywhere this cone intersects with the ground creates what's known as the boom carpet, a path on the surface where the sonic boom can be heard. The sonic boom itself actually consists of two distinct shock waves. The first comes from the nose of the aircraft as it pushes through the air. The second comes from the tail section. To observers on the ground, these two shocks are typically perceived as a sharp double boom, sometimes described as sounding like a double clap of thunder, or the crack of a whip magnified many times over. The pressure signature of these shock waves, when plotted on a graph showing how pressure changes over time, creates a distinctive shape that looks like the letter N. This is why engineers refer to it as an N wave. The overpressure created by a typical sonic boom from a supersonic fighter or transport aircraft ranges from around 1 pound per square foot to 5 pounds per square foot, sometimes more for larger aircraft or certain flight conditions. That might not sound like much, but it's enough to rattle windows, set off car alarms, disturb livestock, and in some cases cause minor structural damage to buildings. More importantly, it's startling. The sudden, unexpected crack of a sonic boom can wake people from sleep, interrupt important activities, and generally make life unpleasant for anyone living beneath regularly used supersonic flight paths. During the 1950s and into the 60s, as the United States Air Force deployed increasing numbers of supersonic fighters for Cold War defense missions, sonic booms became increasingly common across many parts of America. Military pilots needed to train, and that training often involved supersonic flight. The results were predictable. Complaints poured in from citizens whose peace and quiet were regularly shattered by the booms. Some reported cracked plaster, broken windows, and frightened children. Lawsuits were filed. Politicians heard from their constituents. The situation came to a head with the development of supersonic transport aircraft. Both in the United States and abroad, aviation companies and governments invested heavily in developing passenger aircraft that could cruise at supersonic speeds. The British and French collaborated on the Concorde, which would enter service in 1976. The Soviet Union developed the Tupolev Tu-144, and in the United States, Boeing worked on a supersonic transport design that promised to carry hundreds of passengers across oceans at speeds exceeding Mach 2. But there was a problem that couldn't be ignored. If these aircraft were going to operate commercially, flying multiple times per day on regular routes, the sonic boom problem had to be addressed. In 1964, as part of the effort to understand the potential impacts, the Federal Aviation Administration sponsored a series of test flights over Oklahoma City. For 6 months, Air Force and civilian aircraft flew supersonic passes over the city at various times of day, creating intentional sonic booms so that researchers could study public reaction. The results were not encouraging. While some residents tolerated the booms without complaint, many others were deeply disturbed by them. There were reports of broken windows, cracked plaster, and general disruption to daily life. More significantly, a substantial percentage of residents indicated they would not accept such booms on a regular, ongoing basis. The Oklahoma City tests made it clear that unrestricted supersonic flight over populated areas would not be acceptable to the American public. In 1971, under pressure from environmental groups and responding to public concern, the United States Senate voted to cut off funding for the American Supersonic Transport Program. One of the key factors in that decision was the sonic boom issue. That same year, the Federal Aviation Administration issued regulations that effectively banned civil supersonic flight over land within the United States. The ban remains in effect today, more than 50 years later. For the Concorde, this meant that supersonic flight was restricted to routes over water. The aircraft would cruise subsonically over land and only accelerate to supersonic speeds once over the ocean. This limitation significantly reduced the potential markets for the Concorde, and contributed to its limited commercial success. Only 20 production Concords were ever built, and the type was retired from service in 2003 after less than 3 decades of operation. But even as the door closed on civil supersonic flight over land, researchers continued to believe that the problem might not be insurmountable. The sonic boom, they understood, was not some immutable consequence of supersonic flight that had to be accepted as an inevitable side effect. It was a physical phenomenon that could potentially be shaped, managed, and reduced through clever aircraft design. The question was whether theory could be translated into practice, the mathematics of minimization. The theoretical groundwork for reducing sonic booms through aircraft shaping began to emerge in the 1960s and 1970s, driven by researchers who were thinking deeply about the fundamental physics of shockwave formation and propagation. One of the key insights came from understanding that the strength and character of a sonic boom were not solely determined by an aircraft's speed or size, but also by how its volume was distributed along its length. In 1967, a researcher named Wallace Hayes at Princeton University published work exploring the relationship between aircraft shape and sonic boom characteristics. This was followed by important contributions from researchers including A.R. George and Richard Seabass, who in 1971 published a landmark paper that provided a mathematical foundation for sonic boom minimization. Their work showed that under certain idealized conditions, it was theoretically possible to design an aircraft that would produce a much flatter pressure signature, rather than the sharp N wave typically generated by supersonic aircraft. The key was in carefully controlling how the aircraft displaced air as it flew. Instead of having most of the aircraft's volume concentrated in one area, which would create a strong shock wave, the volume could be distributed more gradually along the aircraft's length. The resulting shock waves would be weaker and more spread out. When these waves propagated down to the ground and merged, instead of creating the sharp double bang of a traditional sonic boom, they might create something closer to a gradual rumble or even a shaped signature that would be much less disturbing to people on the ground. This theoretical work was extended by other researchers, including engineers at NASA's Langley Research Center in Virginia. Among the most significant contributors was Christine Darden, an aerospace engineer who had joined NASA in 1967, initially working as what was then called a human computer, performing complex calculations for engineers. Darden, who would later be featured in the book and film Hidden Figures for her groundbreaking work as an African-American woman in aerospace, was promoted to an engineering position in 1973 and assigned to work on the sonic boom problem. Darden's contributions to sonic boom research were extensive and profound. She developed computer codes that could predict how different aircraft shapes would affect sonic boom signatures. One of her key programs was called SEB, named in honor of the work by Seabass and George. SEB could calculate the optimal area distribution for an aircraft designed to minimize sonic boom at specific flight conditions. This was no simple task. The mathematics involved were complex, requiring the program to account for how shock waves would form near the aircraft, how they would propagate through the atmosphere, and how they would eventually be perceived on the ground. Over her 40-year career at NASA, Darden became one of the world's leading experts on sonic boom physics. She earned a doctorate in mechanical engineering from George Washington University in 1983 and eventually rose to become the first African-American woman appointed to the Senior Executive Service at NASA Langley, the highest rank in the Federal Civil Service. By 1989, she was leading NASA's sonic boom team as part of the high-speed research program. She authored more than 50 publications on topics including high lift wing design in supersonic flow, flap design, and critically, sonic boom prediction and minimization. The theoretical work by Darden and her colleagues established what became known as the Jones-Seabass-George-Darden theory of sonic boom minimization. This framework provided the mathematical tools needed to design aircraft that could produce shaped boom signatures. The theory predicted that it should be possible to create what engineers called a flat-top signature, where instead of the sharp pressure spikes of an N wave, the sonic boom would have a more gradual pressure rise, a relatively flat middle section, and a more gradual pressure decrease at the end. But theory and computer predictions, no matter how sophisticated, could only take the research so far. Wind tunnel tests could provide additional validation, but they had their own limitations. What was really needed was a full-scale flight test with an actual aircraft flying at actual supersonic speeds through the actual atmosphere. Only that would prove whether boom shaping could work in the real world. Several factors made such a demonstration difficult. First, modifying an existing aircraft to produce a shaped boom signature was a complex undertaking. The modifications had to be carefully designed using advanced computational fluid dynamics tools. They had to be fabricated to precise specifications, and they had to be flight tested to ensure the modified aircraft could still fly safely. Second, measuring sonic booms required sophisticated instrumentation, both in the air and on the ground. Unlike laboratory experiments where conditions could be carefully controlled, flight testing meant dealing with variable winds, temperature gradients, atmospheric turbulence, and all the other complexities of the real atmosphere. Third, such a program required funding, and during much of the 1980s and 90s, there was limited government or industry appetite for major new supersonic transport programs. The Concorde's commercial struggles and the ban on overland supersonic flight had dampened enthusiasm. It would take a new initiative to revive interest in sonic boom research: DARPA's Quiet Supersonic Vision. That new initiative came at the dawn of the 21st century, driven by the Defense Advanced Research Projects Agency, better known as DARPA. This Pentagon research arm, famous for funding high-risk, high-reward technology programs, saw potential military applications for quieter supersonic aircraft, a reconnaissance vehicle, a medium bomber, or a high-speed transport capable of flying supersonic over land without generating unacceptable sonic booms could provide significant strategic advantages. In 2000, DARPA launched the Quiet Supersonic Platform Program, abbreviated QSP. The program's ambitious goals included developing technologies that would enable supersonic flight over land with boom overpressure rise of less than 0.3 pounds per square foot, dramatically lower than the 1 to 5 pounds per square foot typical of conventional supersonic aircraft. The program also aimed for increased unrefueled range approaching 6,000 nautical miles and improved efficiency compared to existing supersonic aircraft. DARPA structured the QSP program in phases. Phase 1 focused on system integration studies and technology development. On November 9, 2000, DARPA awarded Phase 1 contracts to 3 major aerospace companies: Northrop Grumman, McDonnell Douglas, and Lockheed Martin. Each contract was worth up to $2.5 million and tasked the contractors with developing concepts for quiet supersonic aircraft. Northrop Grumman's integrated systems sector, based in El Segundo, California, approached the QSP program with particular enthusiasm. The company had extensive experience with supersonic aircraft, including the F-5 Freedom Fighter and its improved variant, the F-5E Tiger II. The F-5 family had been one of the most successful export fighters in history, with more than 3,800 F-5s and the closely related T-38 trainers produced. Northrop understood these aircraft intimately, having designed them, built them, and supported them for decades. As part of their Phase 1 QSP work, the Northrop Grumman team began exploring how sonic boom reduction theories could be translated into practical aircraft designs. They studied various configurations, ran computer simulations, and explored the design space for potential solutions. One thing became clear relatively quickly. Before attempting to build a completely new aircraft optimized for low sonic boom, it would be valuable to demonstrate that boom shaping actually worked in flight conditions. This led to the concept that would eventually become the Shaped Sonic Boom Demonstrator. Rather than designing an entirely new aircraft from scratch, which would be enormously expensive and time-consuming, why not modify an existing aircraft to demonstrate the principles of boom shaping? If successful, such a demonstration would validate the theoretical work, prove that CFD tools could accurately predict boom characteristics, and build confidence for future programs. The F-5E Tiger II emerged as an ideal candidate for such a modification. It was a well-understood aircraft. Northrop Grumman had extensive databases on its performance characteristics. The company's facility in St. Augustine, Florida, had decades of experience maintaining and overhauling F-5s for various customers, and critically, F-5Es were still in service with the US Navy and Marine Corps, used as adversary aircraft to help train fighter pilots. This meant that suitable aircraft might be available for a research program. In February 2001, just 3 months after the QSP Phase 1 contracts were awarded, members of Northrop Grumman's integrated product team for the Quiet Supersonic platform began preliminary work on a potential F-5E nose modification. They collaborated with sonic boom experts from Eagle Aeronautics, a small company with deep expertise in boom prediction and analysis. The basic goal was straightforward to state, even if it would prove challenging to achieve: modify the nose of an F-5E in a way that would demonstrably reduce the front shock of its sonic boom signature, while still keeping the aircraft flyable and safe. The design work would end up being far more complex and time-consuming than anyone initially anticipated. What started as a relatively simple concept would evolve through nearly 24 major configurations before arriving at a final design. The process would require cutting-edge computational fluid dynamics, extensive wind tunnel testing, and the creative problem-solving skills of engineers, aerodynamicists, fabrication specialists, and test pilots. But in February 2001, as the team began sketching out preliminary concepts, the long journey toward the Shaped Sonic Boom Demonstrator was just beginning. A design takes shape. The initial concept for modifying the F-5E seemed relatively straightforward. The strongest shockwave in a sonic boom typically comes from the nose of the aircraft, so that's where the modification should be focused. By adding a glove structure over the nose that would change its shape and volume distribution, it should be possible to reduce the strength of that forward shockwave. The design team started with relatively simple linear analysis tools to propose potential nose shapes. These tools were fast and gave quick feedback, making them useful for exploring the design space. Percy Bobbitt from Eagle Aeronautics completed a detailed study in early March 2001, using Euler codes to define an equivalent area distribution for the modified nose. The goal was to generate a flat top pressure signature from 30,000 feet altitude at Mach 1.4. Other team members explored different flight conditions and used different analytical approaches. Hideo Ikawa from Northrop Grumman used a design optimization tool based on Christine Darden's SEB program to calculate an area distribution for Mach 1.55. David Graham converted these results to a Mach 1.0 area distribution, which configuration specialist Jay Vadnais then used to create the initial geometry for what would become the first proposed configuration. Graham verified this design using P-Boom, another suite of linear tools developed at NASA, confirming that it should generate a basically flat-top sonic boom signature. On April 18, 2001, Keith Meredith from Northrop Grumman's Advanced Flight Sciences CFD group completed verification of the near-field effects using higher-order Euler codes. 2 days later, the team submitted their proposal to DARPA to demonstrate sonic boom shaping using this F-5E modification. The initial configuration, which included both a nose glove and an underbody fairing, was designated SBD-01. In July 2001, DARPA awarded the Shaped Sonic Boom Demonstration contract to Northrop Grumman, with funding following in August. Now the real work could begin in earnest. The award of the contract came with the formation of a sonic boom demonstration working group that brought together expertise from across government, industry, and academia. This collaborative approach would prove essential to the program's success. The working group included representatives from NASA's Dryden Flight Research Center at Edwards Air Force Base and NASA's Langley Research Center in Virginia. It included sonic boom experts like Ken Plotkin from Weil Laboratories, whose judgment on predicted boom signatures came to be trusted by everyone involved. It included aerodynamicists from other aerospace companies, including John Morgenstern and Tony Pillon from Lockheed Martin and Todd McGee from Boeing. These representatives not only brought their own expertise, but also ran parallel CFD analyses using their company's proprietary codes, providing valuable independent verification of Northrop Grumman's predictions. The design iteration process that followed was systematic but demanding. Each cycle required several steps. First, specify an area distribution based on the desired sonic boom signature. Second, translate that area distribution into actual aircraft surface geometry. Third, project those surfaces onto a computational grid suitable for CFD analysis. Fourth, run the CFD simulation to calculate how air would flow around the modified aircraft and what shock waves would form. Fifth, validate the CFD results and evaluate the predicted sonic boom signature. Sixth, if needed, correct the area distribution based on what was learned and start the cycle again. Initially, completing this cycle took about 2 weeks. As the team gained experience and refined their procedures, they were able to compress the iteration time to about 3 days. Even so, the design process took considerably longer than initially expected. The team had thought they might need about 6 major design iterations to reach a suitable configuration. Instead, they ended up creating 23 major configurations, with many of those having minor variations, for a total of around 60 different designs examined. The progression of configurations, designated SBD-0, 1 through SBD-25, tells the story of how the design evolved. Early configurations had relatively modest modifications to the nose. As the design matured, the nose glove grew larger and more distinctly shaped. The underbody fairing also evolved, becoming longer and deeper. By the later configurations, the aircraft had taken on its characteristic pelican-like appearance, with the modified nose assembly having roughly doubled in size compared to the original concept. Several factors drove these design changes. One was ensuring that the modification would actually produce the desired shaped boom signature. But equally important was making sure the modified aircraft would still fly safely and have acceptable handling qualities. Adding all that structure to the front of the aircraft moved its center of gravity forward and changed its aerodynamic characteristics. The design team had to ensure the aircraft would remain stable and controllable throughout its flight envelope. Roy Martin, Northrop Grumman's chief test pilot for the program, played a crucial role in this aspect of the design. He recommended limiting the length of the nose glove to match that of a standard F-5F, the 2-seat training version of the F-5E, to avoid excessive lateral instability. He also advised ensuring the width of the nose glove wouldn't interfere with smooth airflow into the engine inlets, which was critical for maintaining engine performance and avoiding inlet buzz or other problems. Martin also suggested optimizing the design for 32,000 feet altitude rather than the 30,000 feet used in some early models. Flying at 32,000 feet would allow a higher Mach number because of lower temperatures at that altitude. It would also permit the chase plane that would be probing the demonstrator's shock waves to stay above 30,000 feet, which was the minimum altitude for Edwards Air Force Base's high-altitude supersonic corridor. One of the more subtle but important aspects of the design involved managing shock waves from sources other than the nose. Wind tunnel tests and flight measurements revealed that shock waves from the wing leading edges and from inlet spillage, where excess air spilled around the engine inlets, could coalesce with the nose shock and affect the overall boom signature. The design team had to account for these effects, which drove some of the changes in the underbody fairing shape. The fairing served multiple purposes. It helped create an area of expansion under the engine inlets, which reduced the pressure of shock waves that would otherwise merge with the bow shock. It also helped manage the overall volume distribution of the aircraft. Getting the fairing geometry right was critical to achieving the desired boom signature. Throughout the design process, the team relied heavily on computational fluid dynamics. The primary CFD code used was called GC and SFV, a sophisticated tool that could account for nonlinear near-field and mid-field shock and expansion effects. Running a single CFD simulation took 10 to 12 hours on the powerful Silicon Graphics computers available at the time. Fortunately, Northrop Grumman's CFD laboratory had spare computer capacity during the SSBD design effort, and the program received strong management support, so computing resources were generally available when needed. The CFD code had to be modified for the SSBD application. Previously, it had typically been used to analyze on-body pressures, predicting how air pressure would vary across an aircraft's surface. For sonic boom work, however, the team needed to predict off-body pressures, calculating how shock waves would propagate away from the aircraft. This required changes to the code and careful validation to ensure it was producing accurate results. Linear analysis tools remained important throughout the design process. These included SEEB, P-Boom, Vorlax, a vortex lattice method, PC-Boom from Weil Labs, and NF-Boom, a propagation code from NASA Ames. Each tool had particular strengths, and using multiple approaches provided valuable cross-checks on the predictions. Christine Darden's SEB code was used consistently throughout the design process, either directly or incorporated with other methods. By early 2002, the design had evolved to what was designated SBD-24B. This configuration was approved at an interim design review held on February 13, 2002, the day after some successful flight tests that validated CFD predictions for shockwave patterns. The design process wasn't quite finished, but SBD-24B represented a major milestone, a configuration that the working group believed could achieve the program's goals. Validating the vision in wind tunnels. While computer simulations were essential for designing the Shaped Sonic Boom Demonstrator, wind tunnel testing remained critical for validating those predictions. No matter how sophisticated CFD tools became, there was no substitute for actually building a physical model and testing it in controlled conditions that simulated supersonic flight. Plans called for testing a scale model of the SSBD configuration in NASA's Glenn Research Center wind tunnel in Ohio. The first test series was scheduled for March 2002. The model chosen was a 5% scale model of an F-5E, about 2.5 feet long, that had been built in the 1970s for weapons integration testing, but apparently never used. The Northrop Grumman team fabricated a miniature nose glove matching the scaled-down geometry of the SBD-24B configuration. This glove could be easily swapped with the model's standard nose, allowing tests of both the baseline and modified configurations. The model had some significant limitations that would soon become problematic. It lacked an internal force balance to directly measure aerodynamic forces and moments acting on it. Its flow-through inlets lacked internal ducting, so air passing through them exited in an uncontrolled manner. Because of concerns about inlet spillage effects on the boom signature, the team installed a mass flow plug behind the model, connected by a fiberglass adapter duct. Changing the model's angle of attack required manually adjusting the mounting bracket, which meant shutting down the tunnel's 87,000 horsepower motors, making the adjustment and restarting everything. The tunnel test plan called for examining both the baseline F-5E and the modified configuration at 3 different Mach numbers: 1.3, 1.35 and 1.4. 3 different angles of attack would be tested at each Mach number. Survey probes at numerous stations along the tunnel walls would collect off-body pressure measurements that could be compared with CFD predictions and used to reconstruct the expected sonic boom signatures. The test required 80 hours of tunnel time, with 20 hours of actual air-on time when the tunnel was operating at test conditions. As those hours passed, it became increasingly clear that something was wrong. The results, to quote the definitive technical report, were disappointing for both the baseline F-5E and the SSBD-24B configuration. The off-body pressures from the baseline F-5E showed unexplained sensitivities to Mach number and significant changes in shockwave characteristics that didn't match expectations. Results with the modified configuration were similarly troubling. At both Mach 1.3 and Mach 1.4, there were unexpected pressure changes affecting the plateau region of the pressure signature that should have created the flat-top boom. Even allowing for expected interference from the model's support structure, there were significant differences between CFD predictions and wind tunnel measurements in terms of shock location and strength. The data were scattered and often not repeatable. Problems with the wind tunnel itself included static pressure variations, off-centerline flow effects, and questionable Mach number and flow angle calibrations. In the cautious language of engineering reports, the conclusion was stark. The results at Glenn did not verify the Shaped Sonic Boom design methodology. The near-field pressure data did not support the CFD predicted signature, and significant model and tunnel data quality issues were identified. This was a serious setback. At the next working group meeting on March 21, 2002, and the preliminary design review on March 26th, the failed wind tunnel test was a major topic of discussion. However, the team was determined not to let this derail the program. The decision was made to attempt another wind tunnel test after correcting as many of the identified problems as possible. Preparing for the second attempt required several months of work. Northrop Grumman specialists improved the model by adding an internal 6-component force and moment balance to directly measure lift, drag, side forces, and moments acting on it. They removed the mass flow plug to reduce interference from extraneous shock waves, inserting wedges in the duct and pressure rakes at the exit instead to control and measure mass flow. They mounted the model on a short sting to move it farther from the strut and its shock waves, and they reduced the strut size to minimize blockage and weaken the shocks it produced. Meanwhile, CFD experts carefully analyzed the effects of the proposed configuration changes before new model components were fabricated. Specialists at Glenn conducted a flow survey of their wind tunnel and examined ways to improve data collection procedures and validity. During this same period, the design team made subtle but important refinements to the configuration itself. Based on continued analysis, they digitally sculpted the aft section of the underbody fairing to a narrower, more tapered shape to improve airflow and reduce the possibility of flow separation. They realigned the angle of the nose assembly to minimize trim drag. CFD modeling confirmed these changes didn't adversely affect the desired boom pressure distribution. This refined design was designated SSBD-24B4 and would be the final configuration. The retest took place during the last week of May 2002. This time the tunnel was operated at Mach 1.367, as close as could be precisely calibrated to the planned flight test speed of Mach 1.4. Only 40 hours of tunnel time were required, half of what the first test had consumed, with 20 hours being actual air-on time. And this time, the results were encouraging. Wind tunnel and CFD pressure distributions for the SSBD configuration showed good correlation over most of the model's length. Wing shock strength and location were correctly predicted when matched with normal force. The results verified the ability of Northrop Grumman's GCNS code to predict off-body pressures of the SSBD configuration to at least 1.5 body lengths from the model. The data also confirmed that moderate changes in Mach number, lift coefficient, and inlet mass flow didn't significantly change near-field pressure signatures. There was still some data scattering, and the correlation near the inlet fell off somewhat, likely because the well-instrumented mass flow plug from the first test had been removed. But overall, the second test was dramatically more successful than the first. The team had learned important lessons about conducting sonic boom wind tunnel experiments. Any models used needed force balances to directly measure forces and moments, and wind tunnels needed to be thoroughly characterized for their flow quality before models were fabricated and tested. With successful wind tunnel validation completed and the design refined to SSBD 24B4, the critical design review was held on July 18, 2002. The meeting approved the final configuration and gave Northrop Grumman authorized to begin physical fabrication of the modified nose and fairing. After more than a year of design work, analysis and testing, it was finally time to build the real thing, bringing the Pelican to life. Translating the digitally optimized shape of the SSBD 24B4 configuration into actual hardware required a combination of advanced manufacturing technology and traditional aerospace craftsmanship. A 15-person vehicle design team led by Keith Applewhite used computer-aided design systems to render the aerodynamic surfaces into the detailed tooling specifications and component drawings needed for fabrication. The outer panels of the nose glove and fairings would be made from composite materials, specifically a carbon fiber fabric pre-impregnated with resin called LTM45EL. This was a cost-effective material for prototypes and low-volume production because it didn't require curing at extremely high temperatures and pressures. However, it had temperature limitations, tolerating no more than 250 degrees Fahrenheit. Internal structure would use aluminum frames and stringers. One of the first steps in the CAD process was smoothing out minor imperfections in the fit and finish of the original CFD-generated geometry. At supersonic speeds, even small surface irregularities could affect airflow, so the outer mold line had to be precisely formed and finished. The design team continued making relatively minor tweaks over the coming months as additional analysis revealed opportunities for improvement. CFD was used to investigate the off-body pressure effects of individual components, like the nose-mounted pitot probe that would measure airspeed. The team analysed spillage from the aircraft's environmental control system inlet, wing lift effects, and horizontal tail angles. Seemingly mundane but essential features like nose gear doors, drainage arrangements, and environmental control system exhaust ducting all required careful design work. The environmental control system exhaust was particularly critical because it would vent hot air that could potentially damage the composite fairings. The design team devised a stainless steel exhaust system and used CFD to model its geometry, surface flow, and cooling capacity. As an additional safety measure, they decided to install thermal switches inside the fairing to alert the pilot if dangerous heat buildup occurred. The actual fabrication took place at Northrop Grumman's Advanced Composites Manufacturing Center in El Segundo. Leading the fabrication team was Mark Smith, a manufacturing engineer who had begun his career with Northrop in 1973, coincidentally working on F-5 production. The team followed rapid prototyping procedures that Northrop Grumman had successfully used for previous projects. Initial fabrication began in July 2002 in Building 905 at the El Segundo facility. Some of the first steps involved creating foam tooling that would serve as templates for laminating the composite panels. These panels would form the outer skin of the nose glove and fairings. Eventually, 33 precisely engineered panels of various sizes would be needed to cover the entire exterior of the modification. The process was methodical but labor-intensive. Each panel had to be laid up by hand, with multiple layers of pre-impregnated carbon fiber fabric carefully positioned over the foam tooling. The resin had to cure properly. The finished panels had to be trimmed and prepared for installation. Internal aluminum structure, including bulkheads and stringers, had to be fabricated to precise specifications and assembled into a framework that would both support the external panels and attach securely to the existing F-5E airframe. As with the aerodynamic design process, fabrication became more complicated and time-consuming than originally planned. Making all the required parts and getting them to fit together properly took months of skilled work. But gradually, the components began to take shape. While fabrication was underway in California, preparations were being made in Florida to receive the parts and install them on an actual F-5E. Northrop Grumman's maintenance depot in St. Augustine had been selected as the location for the modification work. The facility, located at the St. Johns County Airport, had unequaled experience with F-5 aircraft, having overhauled and refurbished numerous Navy and Marine Corps F-5s over the years. The technicians and mechanics there knew these aircraft intimately. Now all that was needed was an actual aircraft to modify. This turned out to be a more complex undertaking than it might sound. Obtaining the Tiger, getting a suitable F-5E for the Shaped Sonic Boom Demonstrator program required navigating military bureaucracy, negotiating agreements, and ensuring that all the various stakeholders' concerns were addressed. The US Navy still operated F-5s through aggressor squadrons that provided adversary training for fighter pilots. Northrop Grumman needed to borrow one of these aircraft, modify it extensively, use it for flight testing, and potentially return it afterward. The key mechanism for arranging this would be a Cooperative Research and Development Agreement, or CRADA, essentially a contract between a federal entity and a non-federal entity to facilitate joint research and development projects. Mike Ingalls, Northrop Grumman St. Augustine's Aircraft Overhaul Program Manager, took the lead in working with Navy officials to make this happen. His excellent relationships with key people in the Naval Air Systems Command, known as NAVAIR, proved invaluable. In January 2002, Ingalls informally approached NAVAIR officials about borrowing and modifying an F-5E for the SSBD. The response was encouraging, so Joe Pawlowski, the SSBD program manager at Northrop Grumman, drafted a formal request. It was co-signed by retired Rear Admiral Stephen Briggs, who was Vice President of the NGC Air Combat Systems Division, and Ingalls delivered it to NAVAIR's Program Management Office in late January. In March 2002, after Pawlowski explained the program in more detail to Rear Admiral Timothy Healy of the Naval Air Warfare Center's Aircraft Division, a full-scale briefing was arranged for Vice Admiral Joseph Dyer, the NAVAIR commander. Dyer was an ideal audience for such a briefing. He was very knowledgeable about technical and safety aspects of experimental projects, having formerly been the Navy's chief test pilot and chief aviation engineer. The briefing, held on March 22nd, included Lisa Vitch from DARPA, Peter Cohen from NASA, and Charles Boccadoro, Stephen Briggs, and Joe Pawlowski from Northrop Grumman. After Veitch introduced the QSP program, and Pawlowski described the planned Shaped Sonic Boom Demonstration, Admiral Dyer responded favourably. He set 3 conditions: having a Navy test pilot fly some of the sorties, meeting all Navy flight clearance criteria, and giving the Navy more involvement in the overall QSP program, especially any follow-on phases. The Navy's tentative approval allowed DARPA's Richard Lezian to make a positive go-no-go decision on the SSBD at the preliminary design review held on March 26, 2002. But tentative approval wasn't the same as having an aircraft in hand. Negotiating the actual terms of the CRADA took months. There were discussions with the Navy's Type Command in New Orleans, which was responsible for operating F-5 type aircraft. Since the planned purchase of surplus F-5s from Switzerland wasn't yet final, the Navy initially wanted the modified aircraft restored to its original condition after the demonstration. Joe Pawlowski and other Northrop Grumman personnel made multiple trips to Naval Air Systems Command headquarters at Patuxent River, Maryland, to negotiate CRADA terms and work with Navarre specialists on the flight clearance process. Finally, on December 10, 2002, Admirals Dyer and Healy and Barbara Olson from Northrop Grumman's subcontracts office signed the CRADA. Pawlowski immediately notified the working group with the good news. The F-5E chosen for modification was identified as Bureau Number 74, 1519, abbreviated BUNO 74, 1519 in Navy parlance. The first 2 digits indicated it had been built in 1974. It came from the U.S. Marine Corps Aggressor Squadron at Yuma, Arizona. The aircraft was due for a major overhaul, but Navarre authorized a 50-hour lifetime extension, reasoning that the SSBD demonstration would put only minimal stresses on the airframe. Roy Martin, Northrop Grumman's chief test pilot, conducted functional check flights on December 17th and 18th, 2002. The first flight revealed some minor handling abnormalities, but after mechanics replaced some parts, Martin was able to make several runs along the supersonic corridor off the Florida coast. Instead of the expected Mach 1.55 maximum speed, the aircraft could only achieve Mach 1.4 at 32,000 feet. The temperature at that altitude measured negative 41 degrees Fahrenheit, compared to the standard day value of negative 48 degrees. The warmer than standard air meant lower air density and higher speed of sound, both of which reduced the aircraft's maximum Mach number. Martin and David Graham still hope to achieve the planned Mach 1.4 during tests at Edwards by using a pushover maneuver from higher altitude to gain additional speed. After further analysis, the team concluded that the unmodified aircraft's Mach 1.4 limitation on a hot day wasn't a showstopper. The modifications would add some drag, but careful flight planning should still allow the necessary test conditions to be achieved. On January 9, 2003, the old F-5E was towed into Northrop Grumman St. Augustine's Hangar 40 to begin its transformation. Then, in early February, Navarre provided welcome news. The last of 4 congressional committees had approved the Navy's purchase of surplus F-5s from Switzerland. This meant that after the SSBD demonstration, the modified aircraft would not need to be restored to standard configuration. It was a small piece of good news, but one that simplified future planning considerably. The transformation. The modification team in St. Augustine, led by Dale Brownlow, began preparing the F-5E for its transformation in the second half of January 2003 by removing its existing nose section. Meanwhile, across the country in El Segundo, Mark Smith and his fabrication team were putting together the sub-assemblies. This included constructing aluminum bulkheads and internal braces and aligning them in a nose assembly tool that served as a template. The careful work of laying up the composite panels continued. Multiple layers of LTM45 EL carbon fiber fabric were positioned over tooling forms, then allowed to cure. Once cured, the panels were removed from the tooling, trimmed to final dimensions, and prepared for attachment to the internal framework. The same material would be used on scaled composites, Spaceship One, that would win the X Prize for achieving the first private sector suborbital flights in 2004, demonstrating the material's suitability for demanding aerospace applications. Fabrication of the nose section was completed in mid-March 2003. The completed nose assembly was carefully packaged for shipment. The underbody fairing was completed on March 17th. Both components were then transported from California to Florida. The photograph of the newly delivered part sitting in Hangar 40 on April 3, 2003, captures a significant moment. The project was transitioning from design and fabrication to actual aircraft modification. To some extent, what was about to happen was equivalent to handcrafting a new prototype. This was not routine maintenance or a standard modification. This was taking a nearly 30-year-old fighter jet and transforming it into a unique research aircraft. Mark Smith and 3 technicians from El Segundo traveled to St. Augustine to augment the local workforce. Charles Boccadoro and Joe Pawlowski from Northrop Grumman's management took turns spending extended periods in Florida, overseeing the work and keeping headquarters informed of progress. The modification work soon encountered challenges that tested the team's ingenuity. One of the more tedious issues involved mating the new nose glove and fairing to the existing F-5 structure. A complex arrangement of bulkheads and aluminum stringers formed the skeleton for the modified exterior. The fabrication design team had configured this framework based on Northrop Grumman's files of F-5E plans and specifications, assuming it would attach easily to a production aircraft structure. But Buno 74 1519 had undergone a lot of field maintenance and several overhauls over its nearly 3 decades of service. Many minor changes had been made, and not all of them were documented in available maintenance records. The aircraft's actual structure deviated in small but significant ways from the standard drawings. As a result, about 90% of the shims and spacers shipped from El Segundo didn't quite line up where they were supposed to. The St. Augustine technicians had to improvise, hand-fitting new connectors to make everything work. On April evening in 2003, Charles Boccadoro was driving back to his hotel on a narrow country road when he swerved to avoid a drunk driver. His rental car crashed into a drainage ditch. When he regained consciousness, the engine compartment was on fire. Despite a badly injured kneecap, he managed to pull himself out through a window and get away before the passenger compartment was engulfed. Emergency personnel arrived, and Boccadoro's biggest concern was retrieving his laptop computer. Fortunately, a skilled doctor in Jacksonville helped him begin rehabilitation, and even the data on his charred computer's hard drive proved recoverable. The accident may have garnered Boccadoro some sympathy at corporate headquarters, where there had been growing concern about the program's delays and cost overruns. Fortunately, the SSBD continued to receive strong support from Scott Seymour, Boccadoro's superior at Northrop Grumman's Integrated Systems sector, which helped sustain the program through its challenges. In addition to the external shape modifications, much of the F-5 SSBD's internal equipment was replaced or relocated. The modification team removed the radar antenna, both 20mm cannons and their ammunition boxes, the lead computing optical sight system, and the fire control computer. This was, after all, no longer a combat aircraft. It was now a flying laboratory dedicated to sonic boom research. The team installed a sophisticated pitot-static probe on the point of the new nose to measure airspeed and pressure. They relocated the battery, tactical air control antenna, and UHF identification friend or foe antenna to different parts of the aircraft, a suite of specialized flight test instrumentation was installed, planned by Ed Herring and colleagues at NASA Dryden. Key among the instrumentation was an Ashtec Z12 carrier phase differential GPS receiver. This sophisticated unit would determine the aircraft's exact position relative to similarly equipped aircraft and ground stations, critical for correlating boom measurements with aircraft position and flight conditions. Northrop Grumman specialists integrated the receiver into a package that fit in the map case on the right side of the cockpit, measuring speed, acceleration, heading, pitch, roll, yaw, and other aerodynamic parameters required an array of sensitive instruments. These included a calibrated Mach meter, temperature-controlled air data transducers, an unheated outside air temperature probe with associated signal conditioning equipment, a 3-axis rate gyroscope, sensitive accelerometers, and various signal conditioning and power control modules. An S-band telemetry transmitter would send data to ground stations during flight tests. Timecode generators and recorders would ensure all data were precisely synchronized. To record pilot comments and cockpit instrument readings, 2 small lipstick video cameras were installed. These connected to a multi-deck 8mm airborne video and voice recorder mounted in the right side gun bay. The telemetry system would allow real-time monitoring and ground recording, while the onboard system would provide backup. Since the St. Augustine facility normally conducted only routine flights of aircraft it overhauled, it didn't have the antennas or ground equipment needed to receive and record flight test telemetry. Northrop Grumman had to install a special ground telemetry station, including a microwave antenna mounted on the hangar roof and an S-band receiver with related processors, displays, recorders, and printers. Federal Communications Commission clearances had to be obtained in advance for the radio frequencies that would be used. Most of the instrumentation was installed and wired by late April. On April 28, 2003, the modified F-5 was towed to the painting facility. 1 week later, it emerged in its distinctive white livery with the red and blue sonic boom pinstripes. The design was the clever inspiration of Northrop Grumman engineer Joan Yazajian, providing a visual representation of the program's purpose that would make the aircraft immediately recognizable. The transformation appeared complete, but during preparations for the first high-speed taxi test on June 9th, inspectors noticed unacceptable play in the nose landing gear doors. The existing clamshell doors had been integrated into the new fairing using the same hinges and an extended actuation arm. This seemingly simple mechanical connection was proving problematic. Solving the nose gear door issue took the rest of June. Mark Smith, who had taken over leading the modification team after Dow Brownlow's retirement in May, brought in 3 technicians who had fabricated the nose in El Segundo to help make the necessary fixes. One of their solutions involved securing the clamshell doors with segments of piano hinge, an elegant if improvised fix. The delay almost created an awkward situation regarding the chase plane for the eventual ferry flight to California. Roy Martin had wanted another F-5 type aircraft, ideally a T-38 for this role. Charles Boccadoro arranged for Boeing to provide a T-38 as part of their data-sharing agreement. Boeing test pilot Mike Bryan flew to St. Augustine in early June, but when it became obvious the nose gear wouldn't be fixed soon, the time came to notify Boeing of the delay. Just before that happened, Bryan received a call from his Boeing office saying the T-38 was needed back in Seattle anyway. He would return a month later when the F-5 SSBD was finally ready to fly. By late July 2003, after months of design work, fabrication and modification, countless hours of skilled labor by technicians and engineers, and perseverance through numerous challenges, the Shaped Sonic Boom Demonstrator was nearly ready for flight testing. But before Roy Martin could take the transformed aircraft into the air, one more critical process had to be completed. obtaining formal flight clearance from the Navy. Clearing the aircraft for flight. Planning for flight operations had proceeded in parallel with the fabrication and modification work throughout 2002 and into 2003. Because the Navy owned the aircraft, they were responsible for flight safety, which meant the planning process was rigorous and systematic. More than 50 NAVAIR specialists and officials would ultimately be involved in reviewing and supporting the SSBD project. Steve Madison was Northrop Grumman's flight test engineer for the program. With inputs from members of the working group and others, he compiled all the requirements for preparing for and conducting the demonstration. These preparations were regularly briefed, updated, and reviewed both internally and by NAVAIR, which also assessed a detailed design analysis of the SSBD modification. The planning documents and briefings covered an extensive range of topics. Governing directives specified which regulations and standards would be followed. Inspection procedures detailed how the aircraft and its systems would be checked. Quality assurance criteria ensured all work met required standards. Certification standards defined what had to be verified before flight. Personnel qualifications specified who could perform various tasks. And of course, the instrumentation plan detailed all the sensors and recording equipment and how they would be installed, calibrated, and operated. The plan specified the sequence of actions for ground checks, envelope expansion flights, functional check flights, and finally the sonic boom data collection flights themselves. Early versions of the test plan were posted on the SSBD website in October 2002. NASA Dryden published a related document covering the in-flight near-field probe measurements that would be performed by their F-15B chase aircraft. In preparing flight profiles, the planners followed a predict, test, analyze philosophy. They used data from the Northrop Grumman subsonic wind tunnel tests and the supersonic tests at Arnold Engineering Development Center, combined with the extensive existing F-5 performance database and CFD analyses, to ensure the modified aircraft would have adequate stability and acceptable handling qualities in all planned flight conditions. Military Standard 1797, covering flying qualities of piloted aircraft, defined detailed criteria that had to be met. Roy Martin, as Chief SSBD test pilot, personally approved each planned maneuver. Northrop Grumman conducted a series of flight readiness reviews covering the aircraft configuration, engineering analysis, test plan, completion of modifications, safety hazard analysis, and other readiness factors. On June 9, 2003, having been reassured by these reviews, NAVAIR formally transmitted its initial flight clearance. The clearance message listed various conditions and constraints the aircraft would comply with. These included flying only in visual meteorological conditions with good weather and visibility. Maximum Mach number was limited to 1.45. The most strenuous approved maneuvers were limited to 3.0 equivalent G-forces. Bank angles couldn't exceed 60 degrees in turns. There would be no abrupt changes in pitch, roll, or yaw. These restrictions ensured the aircraft would be operated well within its demonstrated capabilities. 2 days after receiving initial flight clearance, the nose gear door problem was discovered, grounding the aircraft before it could fly. But ground operations were still possible. On June 9th, Roy Martin took the F-5 SSBD out onto the St. John's runway for its first ground test. 2 subsequent tests on July 23rd checked various systems and verified the aircraft's behavior during acceleration. Keeping below the F-5's takeoff speed of 150 knots, these taxi runs tested brakes at various speeds and distances. On one run, the drag chute was deployed to simulate an abort at 130 knots. These operations also previewed functioning of the air data instrumentation, the GPS system, and the telemetry equipment that would be crucial for recording and transmitting flight test data. After resolving the landing gear problem and receiving another Nevada flight clearance on July 3, 2003, final flight readiness reviews could be conducted. These were held before a 9-person board co-chaired by representatives from Northrop, Grumman and Nevada. By late July, all pertinent quality assurance and safety issues had been successfully addressed. On July 23, 2003, after a final ground test that morning verified all systems were functioning properly, Roy Martin climbed into the cockpit of the white aircraft with its distinctive pelican nose and sonic boom pinstripes. The engines started normally. Systems checks came back green. With chase plane and support personnel ready, Martin received clearance for takeoff. The F-5 SSBD accelerated down the runway, and at 150 knots, Martin pulled back on the stick. The nose gear lifted off, followed moments later by the main gear. The Shaped Sonic Boom Demonstrator, conceived in theory, refined through countless design iterations, validated in wind tunnels, meticulously fabricated and installed, was finally airborne. The first flight was deliberately conservative, staying subsonic, checking basic handling qualities, verifying that all systems worked as expected. Martin flew for about an hour, putting the aircraft through gentle maneuvers, getting a feel for how it responded with all the modifications in place. When he brought it back to St. John's and touched down smoothly on the runway, the landing marked a major milestone. The aircraft flew. It handled acceptably. There were no showstoppers. Over the next several days, Martin conducted additional envelope expansion flights, gradually exploring more of the aircraft's performance regime. Each flight built confidence and validated predictions about handling qualities. The aircraft was slightly different from a standard F-5E as expected, but well within acceptable limits. The stability augmentation system worked properly. Control responses were crisp. There were no unexpected surprises. By early August 2003, the F-5 SSBD was ready for its cross-country ferry flight to California. With Mike Bryan in Boeing's T-38 flying chase, Martin took off from Cecil Field and headed west. The flight to Edwards Air Force Base took them across the southern United States, with stops for refueling along the way. For Martin, much of the flight was practice for the upcoming high-altitude supersonic maneuvers. He frequently flew the F-5 SSBD from unusual positions, simulating the forward visibility limitations created by the long nose. When the two aircraft arrived at Edwards and touched down on the famous dry lakebed runway, they joined a legacy of experimental flight that stretched back to Chuck Yeager's sound barrier braking flight in October 1947. Over the following weeks, the F-5 SSBD would conduct the most extensive sonic boom flight research program ever undertaken, validating decades of theoretical work and opening new possibilities for the future of supersonic flight. Measuring the unmeasurable. Edwards Air Force Base was the ideal location for the flight test program. The base sits in the high desert of Southern California, with clear weather for much of the year and controlled airspace that extends for miles in all directions. Most critically, it has one of the few locations in the United States where supersonic flight over land is permitted, thanks to restricted military airspace and the relatively sparse population. The sonic boom measurement program required unprecedented coordination between multiple aircraft and ground systems. The F-5 SSBD would fly supersonic passes at carefully controlled altitudes, speeds, and flight paths. An F-15B research aircraft from NASA Dryden, equipped with specialized instrumentation, would fly in formation with the SSBD, sometimes ahead, sometimes behind, sometimes off to the side, measuring the shockwave patterns in the near field before they had propagated far from the aircraft. On the ground, an array of microphones had been carefully positioned to measure the sonic boom signatures as they reached the surface. These ground measurements were critical because they would show what people would actually hear, not just what existed near the aircraft. Some of these microphones were placed under the expected flight path. Others were positioned at various distances to the side to measure how the boom changed with lateral distance. Each flight had to be meticulously planned. Weather conditions had to be suitable, with clear skies and minimal winds. The aircraft had to fly at precise altitudes and speeds. The GPS systems on both aircraft had to be functioning perfectly to ensure exact position information. Telemetry systems had to be working to provide real-time data to ground stations. The ground microphone arrays had to be properly calibrated and recording. The first series of sonic boom measurement flights took place in late August 2003. These included flights on August 25th, 27th, and 29th. The F-5 SSBD would climb to altitude, accelerate to supersonic speed, and then perform carefully controlled supersonic passes, while the F-15B measured its shock waves and ground sensors recorded the boom signatures reaching the surface. For comparison purposes, some of the flights also included passes by an unmodified Navy F-5E, allowing direct measurement of the difference between the standard boom signature and the shaped signature produced by the modified aircraft. This was crucial for demonstrating that the modification actually worked as intended. The experience of flying the F-5 SSBD on these test missions was unique. Roy Martin had thousands of hours of flight experience, including extensive time in F-5S, but this aircraft was different. The long nose changed the view from the cockpit. The added weight up front and the modified aerodynamics meant the aircraft handled slightly differently than a standard F-5E, but the modifications had been well designed. The aircraft was stable and controllable. Martin could fly the precise profiles required for the sonic boom measurements. During each supersonic pass, both aircraft were transmitting data in real time. Engineers on the ground could monitor airspeed, altitude, heading, angle of attack, and numerous other parameters. They could see whether the aircraft were on the correct flight path. They could make real-time decisions about whether to repeat a pass or adjust parameters for the next run. The F-15B chase plane carried specialized sensors on a nose boom to measure pressure fluctuations in the shock waves. The pilot would position the F-15B at specific locations relative to the F-5 SSBD, holding formation while data were collected. This was demanding flying, requiring both pilots to maintain precise positions and speeds while traveling faster than the speed of sound. After each flight, teams of engineers would begin analyzing the data. Pressure measurements from the near-field sensors and ground microphones were compared with predictions from computational models. GPS data were processed to determine the exact positions and velocities of the aircraft. Video from the cockpit cameras was reviewed. Telemetry recordings were examined in detail. The initial results were encouraging but not definitive. Analysis of sonic boom data is complex, requiring careful processing to separate the actual boom signature from noise, atmospheric effects, and measurement artifacts. Each flight added more data points. Each analysis refined the understanding of what was being measured. A second series of flights took place in January 2004. These flights built on lessons learned from the August series, with refinements to flight profiles and measurement techniques. In total, approximately 30 test flights were conducted. Each flight added to the body of evidence about whether boom shaping worked. Throughout the test program, safety remained the top priority. Each flight was carefully reviewed beforehand. Weather conditions had to meet strict criteria. Aircraft systems had to be functioning normally. Any anomalies or concerns would result in a flight being delayed or cancelled. The program couldn't afford to lose the one-of-a-kind SSBD aircraft to an accident. The collaboration between organizations was remarkable. NASA Dryden provided the F-15B and its expert pilots and engineers. DARPA provided funding and oversight. Northrop Grumman provided the SSBD aircraft and Roy Martin's piloting expertise, while laboratories provided sonic boom analysis expertise. Members of the working group from Lockheed Martin and Boeing contributed their insights and analysis capabilities. Everyone was working toward the same goal, proving that sonic boom shaping could work. By the time the flight test program concluded in early 2004, more than 1,300 sonic boom recordings had been collected. These included measurements in the near field by the F-15B probe aircraft, measurements on the ground directly under the flight path, and measurements at various lateral distances. The data set was unprecedented in its scope and quality. Now came perhaps the most critical phase of the entire program, analyzing all that data to determine whether the Shaped Sonic Boom Demonstrator had achieved its goal. The results speak. The analysis of sonic boom data from the SSBD flight tests was a painstaking process that took months. Engineers and scientists had to carefully process the recordings, correcting for measurement artifacts, accounting for atmospheric conditions, and comparing the results with computational predictions. The ground-based measurements provided the clearest evidence. When a standard F-5E flew supersonic passes over the microphone array, the recorded signatures showed the characteristic N-wave shape, a sharp rise in pressure at the front shock, followed by a sharp drop at the rear shock, with a relatively linear region in between. The duration was brief, typically less than a second, but the sharp pressure changes created the startling boom that people found objectionable. When the F-5 SSBD flew similar passes, the signatures looked different. The front shock showed a noticeably reduced pressure rise. The middle portion of the signature had the flatter characteristic that theory had predicted. The overall peak overpressure was measurably lower than that of the standard F-5E. Quantitative analysis confirmed what was visible in the waveforms. The SSBD had achieved approximately a 1/3 reduction in perceived loudness compared to the unmodified F-5E under comparable flight conditions. This was a significant result. It demonstrated that boom shaping worked not just in computer simulations or wind tunnel tests, but in actual flight through the real atmosphere with all its complexities. The near-field measurements from the F-15B probe aircraft provided additional validation. By measuring shockwave patterns at various distances and orientations from the SSBD, these data showed how the shaped shockwaves evolved as they propagated away from the aircraft. The measurements matched computational predictions remarkably well, giving confidence that the CFD tools were accurately modeling the physics. Different flight conditions were explored during the test program. The SSBD flew at different altitudes, different speeds, and different lift coefficients. The data showed that the boom reduction was maintained across a range of conditions, not just at one ideal flight state. This was important for practical applications. A future aircraft designed for shaped booms would need to maintain acceptable signatures throughout its operational envelope. The success of the SSBD program validated several key elements that had been uncertain before the flights. First, it confirmed that boom shaping through aircraft geometry was feasible. This wasn't just a theoretical possibility, it actually worked. Second, it demonstrated that modern CFD tools could accurately predict sonic boom signatures, at least for relatively simple configurations like the modified F-5E. This gave confidence for using these tools to design future low-boom aircraft. Third, the program showed that it was possible to design, fabricate, and fly a boom-shaped aircraft using existing technology and materials. The challenges had been significant, but they had been overcome. There were no fundamental barriers preventing the development of larger, more capable aircraft with shaped boom characteristics. The SSBD results were documented in numerous technical papers and presentations. Kenneth Plotkin from Weil Laboratories, Ed Herring from NASA Dryden, David Graham from Northrop Grumman, and many others contributed to publications describing the design process, the flight tests, and the analysis of results. These papers became important references for subsequent sonic boom research. The program also identified areas where more work was needed. The SSBD had demonstrated boom shaping for the front shock, but it hadn't addressed the rear shock from the tail and engine exhaust. A complete low-boom aircraft would need to manage both the front and rear shocks. The SSBD was also a relatively small aircraft. Scaling up to larger transport-sized aircraft would introduce new challenges. Atmospheric effects remained an area of uncertainty. The atmosphere is not uniform or steady. Temperature variations, wind shear, turbulence, and other phenomena can affect how shock waves propagate and what signatures reach the ground. The SSBD flights had encountered typical atmospheric variability, and the boom reduction had been maintained, but more data would be needed to fully understand all the factors involved. Still, the overall verdict was clear. The Shaped Sonic Boom Demonstrator had succeeded. After decades of theoretical work, after months of intensive design and fabrication effort, after extensive testing in wind tunnels and in flight, the program had proven that sonic booms could be shaped and reduced through aircraft design. The door to quiet supersonic flight over land had been opened, at least a crack. Legacy and the path forward. The successful conclusion of the Shaped Sonic Boom Demonstrator program in 2004 marked a turning point in supersonic research. For the first time, there was definitive proof that boom shaping worked in practice, not just in theory. This opened new possibilities for both military and commercial supersonic aviation. Within NASA, the SSBD results energized ongoing research programs. The space agency continued exploring low-boom concepts, conducting wind tunnel tests of various configurations, refining computational tools, and planning for future demonstration flights. The goal was to develop technologies that would enable a new generation of supersonic transport aircraft capable of flying over land without generating unacceptable sonic booms. In 2016, NASA announced a new initiative called the Low Boom Flight Demonstrator, later renamed the X-59 QuESTI, Quiet Supersonic Technology. This would be a purpose-built research aircraft designed from the outset to produce a shaped sonic boom. Unlike the SSBD, which was a modification of an existing fighter, the X-59 would be an entirely new aircraft optimized for low boom characteristics. Lockheed Martin's Skunk Works was selected to design and build the X-59. The aircraft features an extremely long, slender nose, careful shaping of its fuselage and wings, and engines mounted on top of the fuselage, all intended to minimize and shape the shock waves it produces. The goal is to reduce the sonic boom to something more like a soft thump, with peak overpressures around 75 perceived decibels, compared to the 105 decibels of the Concorde. The X-59 program builds directly on the foundation established by the SSBD. Many of the computational tools, design methods, and testing techniques pioneered during the SSBD program inform the X-59's development. The confidence gained from the SSBD's success gave NASA and its partners the assurance to invest in the much larger and more ambitious X-59 project. As of this recording, the X-59 is in final stages of ground testing and preparation for first flight. Once flying, it will conduct flight tests over various communities to measure public response to its shaped boom signature. These community overflights will provide critical data for regulators considering whether to modify or lift the current ban on supersonic flight over land. The potential economic and societal impact of enabling supersonic flight over land is substantial. Business travelers could reach distant destinations in half the time or less. emergency medical and relief flights could deliver personnel and supplies much faster. The aviation industry could see new markets open for supersonic business jets and eventually larger passenger transports. Several private companies are developing supersonic business jet concepts, including Boom Supersonic, Spike Aerospace, and Aerion Supersonic. These ventures are betting that shaped boom technology, combined with modern engine and materials technology, can finally make supersonic travel commercially viable for a broader market than the Concorde served. Military planners remain interested as well. The ability to fly supersonic over land without generating unacceptable booms would provide new options for rapid response, reconnaissance, and strike missions. Aircraft could reach targets or crisis zones much faster, potentially changing the calculus of military operations. But significant challenges remain before any of these possibilities become routine reality. Engine technology needs to continue advancing to provide supersonic cruise capability with acceptable fuel consumption and noise during takeoff and landing. Materials and manufacturing technologies must enable cost-effective production of the complex shapes required for low-boom aircraft. Most critically, regulators must develop new rules that define acceptable sonic boom levels and provide certification standards for low-boom aircraft. The SSBD program demonstrated that boom shaping is technically feasible. What remains to be answered is whether it's economically and politically feasible to develop and operate such aircraft on a large scale. Remembering the people. Behind every technical achievement, there are people whose dedication, creativity, and perseverance make success possible. The Shaped Sonic Boom Demonstrator program was no exception. Roy Martin, the chief test pilot, exemplified the skilled professionalism required for experimental flight testing. He wasn't just along for the ride. His insights during the design process, his careful evaluation of the aircraft's handling qualities, and his precise flying during the sonic boom measurements were essential to the program's success. Every time he climbed into that white aircraft with the pelican nose, he was accepting risk to advance knowledge. David Graham, the chief aerodynamicist, guided the design through its many iterations. His understanding of both the theoretical principles and the practical challenges of creating a boom-shaped aircraft helped translate abstract concepts into actual hardware. His patience during the long design process, with its dead ends and setbacks, helped keep the team focused on the ultimate goal. Christine Darden's theoretical work, conducted over decades at NASA Langley, provided the foundation that made the SSBD possible. Her SEB code was used throughout the design process. Her insights into boom minimization physics informed the approach. That a woman who had started as a human computer in the 1960s would make such fundamental contributions to aerospace engineering speaks to both her brilliance and her determination to overcome barriers. Ken Plotkin from Weil Laboratories brought deep expertise in sonic boom physics and measurement. His judgment on predicted boom signatures was trusted by everyone involved. His analysis of the flight test data helped extract meaningful conclusions from the complex measurements. The fabrication team led by Mark Smith transformed digital designs into physical reality. Their craftsmanship in laying up composite panels, fabricating metal components, and assembling everything into a flyable aircraft demonstrated that even in an age of advanced computer tools, skilled hands and experienced judgment remain essential. The modification team in St. Augustine, including Dale Brownlow before his retirement, and the numerous technicians and mechanics who did the actual work of transforming Buno 74, 1519, showed the kind of perseverance required for one-of-a-kind projects. When the planned procedures didn't work, they improvised. When parts didn't fit quite right, they handcrafted solutions. They took pride in their work, knowing they were contributing to something significant. Charles Boccadoro and Joe Pawlowski, who managed the program through its various phases, dealt with budgets, schedules, bureaucratic requirements, and all the administrative challenges that accompany a high-visibility research program. Their persistence in working through the Navy CRADA process, their support of the team during difficult periods, and their advocacy for the program within Northrop Grumman helped keep it on track. Ed Herring at NASA Dryden coordinated the sophisticated instrumentation systems and the F-15B probe aircraft operations. His expertise in flight test measurement techniques ensured that high-quality data were collected during the sonic boom flights. The members of the Sonic Boom Demonstration Working Group, including representatives from NASA Langley and Dryden, DARPA, Weil Labs, Lockheed Martin, and Boeing, provided collaborative expertise that enriched the program. Their willingness to share insights, run independent analyses, and contribute to the collective understanding exemplified the best aspects of scientific and engineering collaboration. Behind all these individuals were family members who supported their work, sometimes through long absences during critical program phases. There were colleagues who handled other tasks so team members could focus on SSBD work. There were support staff who managed logistics, paperwork, and countless details. Large programs succeed because many people contribute, even though only a few names end up in the historical record. The SSBD program also demonstrated something important about how complex engineering projects can succeed. The collaborative structure, with the working group bringing together diverse expertise, allowed problems to be solved more effectively than any single organization could have managed alone. The systematic design process, with its iterative cycles of design, analysis, and refinement, showed the value of patience and thoroughness. The use of multiple independent analyses and validation methods helped catch errors and build confidence. These lessons extend beyond sonic boom research to other challenging engineering endeavors. Complex problems often require collaboration across organizations. Theoretical work must be validated through testing. Sophisticated tools are valuable, but experienced judgment remains essential. Setbacks and failures are opportunities to learn and improve. Perseverance matters as much as cleverness, the sound of the future. As we look toward the future of aviation, the question of supersonic flight over land remains unresolved. The SSBD demonstrated that boom shaping works. The X-59 program aims to demonstrate it at a larger scale with even better boom reduction. But demonstrating technical feasibility is not the same as achieving regulatory approval, economic viability, and public acceptance. The regulatory framework needs to evolve. Current rules simply prohibit supersonic flight over land. Future rules will need to define acceptable boom levels in quantitative terms, establish certification procedures for verifying that aircraft meet those standards, and provide guidelines for where and when supersonic flight would be permitted. This will require input from noise experts, aviation regulators, aircraft manufacturers, airline operators, and the public. Economic factors will play a crucial role. Designing and building shaped boom aircraft costs money. Operating them costs money. Passengers or cargo customers will need to be willing to pay premiums for speed. The market needs to be large enough to support aircraft production in sufficient quantities to bring costs down. Airlines need confidence that the regulatory environment won't change after they've invested in aircraft. Public acceptance may be the most challenging factor. People who have never experienced a shaped sonic boom may be skeptical that it's truly less disturbing than a conventional boom. Community overflight tests with the X-59 are designed to address this, but building broad public support for supersonic flight over land will require careful communication and engagement. Environmental considerations add another layer of complexity. Supersonic aircraft burn more fuel per passenger mile than subsonic aircraft. In an era of increasing concern about climate change, This creates tension between the benefits of faster travel and the goal of reducing aviation's carbon footprint. Some argue that truly sustainable supersonic flight will require not just shaped booms, but also new propulsion technologies, sustainable aviation fuels, or even electric or hybrid propulsion systems. Despite these challenges, the potential benefits of supersonic flight continue to motivate research and development. Time is valuable. Being able to travel across continents or oceans in half the time opens new possibilities for business, tourism, family connections, and cultural exchange. Military and emergency response applications could save lives. The economic activity generated by a new class of aircraft could create jobs and drive technological innovation in related fields. The Shaped Sonic Boom Demonstrator took one critical step along this path. It proved that the loud crack of a traditional sonic boom is not an insurmountable barrier to supersonic flight over land. With the right aircraft design, informed by sophisticated computational tools and validated through careful testing, it's possible to dramatically reduce the noise impact of supersonic flight. Whether this technical capability will ultimately translate into routine supersonic travel over land remains to be seen. But thanks to the SSBD program and the decades of work that preceded it, we know it's possible. We know what needs to be done. The question now is whether we, as a society, will choose to pursue that possibility. The story of the Shaped Sonic Boom Demonstrator is ultimately a story about persistence, collaboration, and the belief that challenging problems can be solved through systematic effort. It took decades from the early theoretical work to the successful flight demonstrations. It required contributions from many people across multiple organizations. It survived funding challenges, technical setbacks, and skepticism. On those August days in 2003, when Roy Martin flew the white F-5 with the distinctive pelican nose across the high desert sky, leaving behind a shaped sonic boom that was measurably quieter than that of a conventional supersonic aircraft, decades of effort came to fruition. The thunder that had once shaken a nation had been tamed, at least a little. The skies had been quieted, if only by a few decibels. Perhaps someday in the future, passengers on a supersonic transport will look out their windows at the landscape far below, cruising faster than sound, yet generating no more disturbance than a distant rumble of thunder. If that day comes, it will owe a debt to a peculiar-looking modified F-5E that proved it could be done, and to all the people who believed that the boom could be quieted. Closing. The story we've explored today reminds us that progress in aerospace engineering, like most fields, comes in small steps built on foundations laid by previous generations. The X-1 broke the sound barrier. The Concorde proved supersonic transport could work, if only over water. The SSBD showed that sonic booms could be shaped. The X-59 aims to prove it can be done even better. Each achievement opens the door for the next. Somewhere in the future, perhaps not too many years from now, you might hear a gentle rumble overhead as a sleek aircraft passes at supersonic speed, traveling from one city to another in far less time than today's airliners require. When you hear that sound, remember the white F-5 with the pelican nose that helped make it possible. Remember the engineers, pilots, technicians, and researchers who refused to accept that the sonic boom was an insurmountable barrier. And remember that behind every technical achievement are people with vision, persistence, and the willingness to tackle difficult problems one step at a time. The future of aviation, like its past, will be written by people who believe that challenges exist to be overcome, not as excuses for inaction. If you enjoyed this deep dive into aerospace history and the science of supersonic flight, please consider subscribing to the channel and hitting the like button. Your support helps make these detailed explorations possible. And if you have questions or thoughts about sonic boom research, supersonic flight, or related topics, feel free to leave them in the comments. Until next time, keep looking up at the skies and wondering what might be possible.